Hello everyone, welcome to the second part of this tutorial. I will be going over the setup of the simulation as well as the post-processing of the solution for this given case. So in the last video we went over how to set up the geometry as well as the mesh. Now you can see here that the mesh and the geometry are ready, so we can just go ahead and start our setup. So double click on the setup. And you want to make sure that it's double precision. This would make your solution more accurate. And if you want to use multiple cores from your computer, you can set up the parallel option in here. And for my computer, I want to use 2 of the processes I have. All right, so we have our mesh loaded. Now, like we said earlier, we want to set up the simulation so that it's an axisymmetric case. So we want to make sure that the axisymmetric option is selected. Another thing you want to make sure of is when you're doing supersonic flow simulations, you want to make sure that the solver type is density based. For subsonic flows, you can use a pressure based type solver and you would get accurate results as well. And then finally, one last thing we have to do is we just check our mesh, make sure that we don't have any errors. Sometimes it would show some crucial errors in here, but for this case, I've had this error multiple times and it didn't give me any problems. So I'm just gonna go ahead and continue on with my simulation. All right, so like we said earlier, we're doing a supersonic flow, so we want to make sure that the energy equation is turned on. Since this is a supersonic flow, and for this specific case, it is a turbulent flow. There are a couple of options for the models we can use. You can research those options in a more thoroughly, but for me, what I've been using is either Spalart-Almaraz or K omega SST. Now I've noticed that with Spalart-Almaraz, it works well for for anything below Mach 2. The reason for that being is this specific model was developed for Boeing for the transonic flow regime. Since it's very specific for their cases. Another model that works fairly well and gives fairly accurate results is K omega SST. So I'm going to be using this one for this specific simulation. All right, so on to the materials. We have to make sure that the air settings are changed to be an ideal gas, since this is not a constant density type of flow. Another thing we have to change is we have to make sure that the viscosity is also varying according to either Sutherland's law or power law. So for this case, I'm just gonna be using the Sutherland's law. Right, make sure we change that. Now finally, we have to set up our boundary conditions. So in this case, I will be doing like we selected earlier. This is going to be our pressure inlet, and this is going to be our pressure outlet in here, and this is going to be our axis and the nodes over here. So if you want to know what kind of pressure to put for the pressure inlet option as well as what pressure to use, I will be these links will be in the description. So pretty much for the inlet pressure, we will be using the isentropic flow equations. So your total pressure is going to be the pressure that you will be giving the ANSYS fluent, and you want to make sure that this pressure is in gauge pressure. So this pressure is going to be the sonic conditions, and in this case it's going to be the atmospheric pressure, and the way you get your atmospheric pressure is you look at what altitude you want to investigate the flow at, and then you take the atmospheric pressure at that given altitude. I will be posting this in the description section as well. So for this specific case, I'll be doing the simulation at the 10-kilometer altitude. So you can see here that this is going to be the density, this is going to be the pressure, and this is going to be the density for that specific altitude. And also, it's going to be a flow of Mach 2.92. So I went ahead and did the calculations, and I ended up with with this pressure, and I made sure to subtract the atmospheric pressure so I can get the gauge pressure. Another thing you also have to calculate is the total temperature. Now this is going to be the same case with the previous equation as well, where the total temperature is the temperature you are giving Fluent, and this temperature, or the sonic temperature, is going to be the atmospheric temperature. All right, so I've done the calculation, and these are the values I ended up with. So I'm just going to go ahead and input that into the solver. So for the operating pressure, we have, like I said, this is going to be the pressure at the 10-kilometer altitude. So let's go ahead and input that in here. For the inlet condition, we said we wanted to have a pressure inlet. So I'll go ahead and specify the gauge pressure to be this pressure right here. And just to get make sure that your direction is right, you can actually specify the direction vector for your flow. So in this case, it's just going to be in the positive axial direction. So pretty much going from here in this direction right here. All right. So for the turbulence, you will have to check the atmospheric turbulence intensity at that altitude, as well as the length scale. So for my specific case, these are the values I calculated for the intensity and length scale. All right, and I'm just going to go ahead and input that in here. This was 3.9 e to the negative 4. And we want to make sure we change our temperature option as well. All right. Now we also have to change our pressure outlet options. So, all right. So our temperature is going to be the same one we calculated for the pressure inlet option. And the backflow direction, you want to make sure you have that selected to from the neighboring cell. I have noticed that when this is selected to the normal to boundary option, most of the times it would fail to converge. So it's important that you have this selected to the from neighboring cell option. And the same thing goes for the intensity and the turbulence length scale. We want to make sure we change that to the appropriate values. All right. All right, awesome. So now we have our boundary conditions all set up. So we have another thing we have to do is now we can go to our reference values, compute from inlet. So this is another sanity check you can use to make sure that all your values are right. So my velocity is as I expected, about Mach 2.92, and the temperature in here matches the atmospheric temperature. And I noticed that also it does not change the viscosity So you'd have to change this manually to the atmospheric viscosity at that altitude. Right. Also, another thing you want to change if you are interested in calculating the coefficient of drag is the area. So this is going to be the area of interest or the area of the body you are trying to investigate. So for example, if you are calculating the coefficient of a drag across a fin, you would have the frontal area of the fin in here rather than the frontal area of the entire rocket. But for this specific simulation, I'm just interested in the frontal area of the rocket or the frontal area of the nose cone, which I calculated it to be 0.13 meters squared. And also my reference length is going to be the length of the nose cone, so 2.032 meters. Another thing you want to change is the methods. So to get more accurate solutions, you want to change all your equations to be second order. Another setting you also want to choose is your residuals. So for supersonic flow, it's not enough to have 1 e to the -3. Rather, you would have a more accurate solution if you have lower thresholds for your residuals. So 1 e to the -6 works fairly well. All right. And now, since we said we are interested in the coefficient of drag, so we can go ahead and create a new report. So we go to new, force, then drag. You could also calculate some of the other things. For example, the mass flow rate, or there's a bunch of other quantities in here, but what I'm really interested in is the coefficient of drag. So we have the drag coefficient. Let's go ahead and rename this report. Drag coefficients. And then also you could change the drag coefficient to be the drag type to be either the drag coefficient or the drag force. All right, so our body, or the body that I'm interested in calculating the drag for, is the nose. And I want to make sure that the force vector is right. So the x and the y, so that means it's going in the positive x direction or this direction. All right, and I want to make sure that I have this value selected so I can kind of monitor if my solution has converged or not. All right, the last step is you want to initialize your solution. So you'll go ahead and initialize that from the inlet. All right, everything looks good. Go ahead and initialize it. Now another sanity check you also could use is you go ahead and plot the velocity contours, and instead of selecting velocity magnitude, you could select the velocity or the Mach number. So I'll go ahead and display that. And as you can see here, it's 2.92, which is what I calculated for. So it should be good. And now finally, we can go ahead and run our calculations. So normally I start at 1,000 iterations and see if that converges. Right. Everything looks good. We'll go ahead and click calculate. And this is another reason why I had the options selected for the drag coefficient report. I just want to make sure that the drag coefficient is converging and not diverging. And we can see here our residuals are going down very nicely. So we'll go ahead and let this calculate, and then we will get back to it. All right, so now our solution has finished. We can see here that nothing funky is going on. The solutions are not diverging. And we also saw that the dark coefficient kind of stabilizes after after about 400 iterations. So that should be good. Now, all right. All right, so we got our initial solution. However, this is not our most accurate solution. The reason is, like I said in the last video, we chose the mesh to be um, just fine enough to capture the geometry, but we didn't really care about the boundary layer. So in this method, I will be adapting the mesh so that it kind of captures the boundary layer properly. And we want to make sure that we have a more accurate solution that way. So the way we do that is we go to refine, adapt in here, and then under cell registers we select new. We go to field variable. We want to make sure we have the field value of the velocity magnitude, since that determines the boundary layer. And we want to have the software capture all the cells that have a gradient of more. Okay, let me select these options. We want to make sure that the software captures all the cells that have a velocity magnitude gradient of more than, well, we'll say 1. So you can kind of see what I'm talking about when I click this right here. So you can kind of see here that it selected the cells that have a fairly high difference in between the cells. And you can see here that even if you do your best when you're doing the mesh, for these types of flow, the boundary layer is going to be developing across the geometry. So it's going to be really hard to capture that properly or manually using the different meshing options. So it's easier to just do it this way. All right, so we went ahead and selected our cells, and right, we go under here. We make sure that the gradient option we created is selected. We click display again to make sure it's selecting the right cells, and then we click adapt. All right, so it gave us the number of cells in the original file and the number of cells that are new. So if you are using the student version, you want to make sure that the number of cells is less than 500,000, because that's the student version limitation. I'm not sure if it's the number of cells or the number of nodes, but one of them has to be less than 500,000. All right, so now that we have the mesh adapted, I can show you what that looks like. We can go ahead under the boundary conditions and then display the mesh. So you can see here that these are the cells that the software adapted. All right, so we can go back to the calculation and then recalculate it again to get a better solution. All right, so our solution has finished, and as you can see here that we got a slightly lower coefficient of drag value. We can go ahead and do one more loop of adaption. So we'll go ahead and display what cells need to be adapted. And as you can see here, this is going to be become smaller and smaller every time. So, all right, let me do that again. All right, we got our cells. We'll go ahead and do the adaption. Okay, all right. So my cells and nodes are well below 500,000, so I should be good. All right, I'll go ahead and recalculate the solution. All right, so we have our final calculation all set up. So you can see here that you can go ahead and do more more refinement if you want. But one thing you want to make sure of is you want to make sure that you'll raise the number of maximum refinement levels. For some reason, this is set to 2, so it won't allow you to do any more refinements. So you can see here that if I click display, it's not showing me any cells because it has hit the maximum level, the maximum refinement levels. So just raise that by 1 so it can refine one more time. But like I said, I'm not gonna do that. If you want, you can just go ahead and keep refining until your coefficient of drag converges. So you want to see something like this, where the solution converges. What you don't want to be seeing, I'll do my best to draw it. What you don't want to be seeing is if your solution just kind of starts going up exponentially. That means your solution is diverging, which means you have to go ahead. You have to go back and recheck your mesh, recheck your boundary conditions, make sure that nothing weird is going on. Right, go ahead and clear this. So let's go ahead and create some contours. All right, so we can create contours of the Mach numbers. So we could just click on save display. Okay, we get this very colorful graph. Other contours we can check, we can have the contours of the pressure or the density to better investigate the flow. All right. And also, if you have the contours ready and you want to take a high definition picture of this, you just go to File and then save the picture. Then usually I find PNG to be one of the higher quality format options, but you can go ahead and select any other format option you want. All right, and another thing, if you want to get the exact drag coefficient, you can go ahead and compute that in here. So go to your report and then click compute to get the exact number that Fluent calculated. And all right, well, I think that should do it for this video. If you have any questions about the simulation, please let me know in the comments below and I will do my best to answer them. Thank you.